So I'm going to talk about what I'm currently working on, which is around monitoring, measurement and verification, and thinking about this with regard to CO2 storage. So what I'm going to present here is on behalf of a number of authors that are listed there. And I should say that the consortiums that the work represents are from Project Greensand and also the STEM CCS community. So just a little bit, I'm sure you're aware of the impacts of greenhouse gas emissions are acute. And if we look, I think the latest news is that we're about 1.2 degrees C above pre-industrial average. So the green there is natural and the black is the observed. So this is driven by greenhouse gases, particularly CO2 and water vapors. The CO2 concentrations are now approaching 420 parts per million, whereas in pre-industrial times it's about 280. So there's a serious issue. So one possible solution or one component of solution is around carbon capture and storage. And this is a schematic that in order to capture, transport and store, we need to be assured that the CO2 stays in the subsurface and that we can detect any leakage. And I'm going to talk really around how we go about monitoring CO2 in storage complexes, but also above storage complexes. So measurement, monitoring and verification, or MMV, energy companies that propose CO2 storage, certainly underwater, but also onshore, are required to produce an agreed MMV program with regulators. So being able to monitor a CO2 storage complex over the lifespan of storage and beyond, so that's 25, maybe to 40 years, you need to have a program and a plan. Now there are, in terms of CO2 injection wells and changes in subsurface reservoirs, there are good, well-developed standard industry approaches to this. However, for long-term monitoring of CO2 storage reservoirs, we've needed to come up with novel methodologies to detect, attribute and quantify. So we need to be able to see where the CO2 is, see where it's come from, and in the unlikely event that there is any leakage, to be able to quantify it. So one way that we can detect CO2 in the water column is using chemical sensing. And the group at the National Oceanography Centre in Southampton have done a lot of work on developing micro sensors that can detect a whole range of different nutrients and carbonate parameters. But clearly the most important here are pH and alkalinity. And these chemical sensors can be put on a range of different platforms. So they can be put on gliders, autonomous underwater vehicles, moorings and landers. So chemical sensing is a very good way of detecting dissolved CO2 in the water column. In terms of gaseous CO2, we think that the best way to do this is using active sonar. And I'm just going to illustrate this with one example from some work we did 2 or 3 years ago. So top right, you'll see some multi-beam bathymetry images of a methane plume from a pot mark in the North Sea. And the pot mark is imaged at different times of the tide, and you can see that the methane plume is very clear, and this particular one is forked, as in it has two limbs to the methane plume. What we can do is actually quantify the gas content within this natural plume, and the way we do that is using a range of active sonar devices. So what we do is we map out the extent of the plume using multi-beam echo sounder, so backscatter from that. And then we use additional active sonar, so EK60s and sub-bottom profiler data to get a range of frequency with which we insonify the plume. And what you then do is you look at the backscatter from the methane bubbles at different frequencies at different depths, and then you produce a model and iteratively match the backscatter from the model to the observations. And from this, you can determine the distribution of bubble radii at each depth. And from this, you can calculate the total gas flux. So this is applied to methane, but is equally applicable to carbon dioxide. And in fact, we've applied this to natural CO2 plumes. So we can use active sonar in a very straightforward manner to insonify and calculate the amount of gas flux there is within a plume from the seabed. So one of the things that we did a few years ago was an experiment in the North Sea as part of an EU-funded program, STEM CCS. And what we did, I hope you can see my mouse here. So there was a CO2 container placed on the seabed. This is close, essentially northeast of Scotland, in 120 meters of water in the North Sea. So we put a CO2 container on the seabed. We then pushed the pipe into the seabed to a depth of about 4 meters beneath the seabed. We released the CO2, and then we used a whole suite of different sensors on different platforms to see if we could detect the CO2 both within the seabed and within the water column. So this is a way of testing all the technologies that are available. And we use chemical sensing, we use active acoustics on a ship, on an AUV. We do all kinds of fun things in terms of using benthic chambers and optodes to look at detecting the CO2. So this was quite a large logistical operation. So putting a container-sized cylinder of CO2 on the seabed, connecting it all up with an ROV, putting a pipe in. And what we did is we released we put down about 3 tons of liquid CO2 plus some tracers to track it. We could adjust the flow rate using a remotely operated vehicle. And the results of this experiment were published in 2021. And you can look at Flo et al. There in terms of a description of the experiment and the different techniques we used. To cut a long story short, and this is a short talk, what we found was that active and passive acoustics work really well to detect the gas bubbles in the water column. I'm going to talk mainly about active acoustics in this talk. And then chemical sensors was also very effective at detecting the dissolved CO2. We found a number of other technologies might be suitable with further developments. And we did find that some things really weren't suitable for long-term release, such as direct sampling of water or the sediments. So what we now know is that CO2 dissolves rapidly in seawater. And for that reason, bubbles and chemical signatures need to be picked up close to the seabed. So the chemical signatures need to be picked up within about 2 or 3 meters of the seabed. And the bubbles will typically dissolve within about, depending on the release rate, but say between 8 and 15 meters above the seabed. So you need to get sensors close to the seabed to be able to see them. Chemistry and active acoustics are highly complementary. So chemistry will detect the dissolve phase. Active acoustics will detect the gaseous phase. And once again, there's a couple of papers there that describe what we did and what we found. Okay, so move to a current project that I'm working on, so Project Greensand. This is a project that's funded by the Danish government and the European Union, and it's around moving to full large-scale CCS storage offshore Denmark. And there's a little map here, top left, where you can see that the position of the storage complex. And this is looking in what's known as a mini area, and the reservoir is sandstone units of Paleocene, Eocene age in a paleo canyon. And there's a whole range of companies and institutions that are partners in this. And I'm really talking about the component from the University of Southampton and the National Oceanography Centre. So the final decision on investment is later this year. They've been doing pilot injection for a number of months now, but full-scale injection and the business decision will be made, I believe, in November. So the leading companies on this are, there's a whole range there, but particularly INEOS and Wintershall Dea, the energy companies. Okay, so what our component of Greensand was to design and implement chemical and acoustic systems for long-term CCS monitoring. So as we described around active acoustics and long-term deployment of chemical systems. So we were tasked to design and deliver a lander to house these sensors that was going to be compatible with multiple power and communication systems. And I can talk more and take questions on that a bit later. And we needed to demonstrate this in harbour and sea trials. So what we did in Southampton is we did in December last year a test deployment of the lander that we built, and it was ready to check that it would fully operate and that we could detect the CO2. So here's a picture of the lander. In brief, it has a communications hub, a battery that will drive the sensors. It's got pH and alkalinity sensors, a nitrate sensor, and here's the active acoustic system. So this is a sonar that, as I'll show you in a minute, looks sideways and sonifies the bubbles. Okay, so here's a picture of what we tested in December. So we're looking to, where my mouse is, we have the quayside. We have a crane, we put the lander down into the dock. We then had a gas cylinder, a pipe that led to the seabed with a perforation on the end, and then we released the CO2 bubbles into the water, and some of these dissolved and some moved up as gas and slowly dissolved. So the active sonar unit looks sideways and insonifies the bubbles as shown here, and then the dissolved CO2 with tidal action, this will move towards the chemical sensors. So what we found with the active acoustics, so for those that are interested, the system we use operated at 500 kilohertz. We think that pinging about every 15 minutes would be applicable to offshore sites. And what you can see here is fairly obvious. So we've got the dockside, we have the sonar image, and we can see a bright spot where we detect the gas bubbles in the water column. So this is the backscatter. We can test this at different ranges. So, and we're currently experimenting with that, but certainly it's very straightforward to detect out to about 150 meters for very small releases of CO2. So 2 liters per minute is quite a small amount, and it's about the smallest amount you can control in terms of getting consistent flow across the seabed. So the active sonar worked very well. If we look at the chemical sensing, what you can do is plot pH against salinity. And what you can see is that after the CO2 release, you see a substantial drop in the pH for the same salinity. So this is a way of telling that that our chemical sensors really pick out the CO2, the dissolved CO2 in the water column. So what we showed in the dock tests is that the system works. We can detect the tides and the CO2, and that relatively small amounts of CO2 released into the water column are readily detectable with chemical and acoustic sensing techniques. And we need to design these into an MMB plan. So the last part of the talk is really, I hope to have a little bit of a discussion. So in terms of monitoring solutions, what we're currently thinking about and talking to energy companies and also regulators is, if you look at this lower image, we either take CO2 from shore with a pipeline, or we have an offshore storage platform and we inject CO2 into a reservoir or aquifer. In terms of leakage pathways, the most likely, obviously you could design multiple barriers to prevent the CO2 coming up. So in the unlikely event that CO2 could emerge, the likely pathways would be from a poorly plugged relic well. And certainly the industry looks very carefully at the way that these old wells are tapped. You might have some concerns about your injection point, so you might want to monitor that. But also old fault might be a position where you might have some concerns, or seabed outcrop of your reservoir formation might be another thing you'd want to monitor. So the type of monitoring solutions we're thinking about are long-term land deployments, imaging the positions of relic wells or release points, And I guess that's our primary advice, would be to have a number of these to look after particularly risky points above your storage complex. But something you can also consider is using an autonomous underwater vehicle to do a wider area survey. One thing to note with this is that in order to get chemical sensing, you need to fly this AUV very close to the seabed, and that could be an issue if you need to get down within 2 or 3 meters, given that there's all this infrastructure on the seabed. Whereas with active acoustics, you could certainly image a gas plume using AUV. So this is my final slide. I'll just spend a bit of time talking to this. So in MMV plans, what will have happened is that an energy company or consortia will have proposed a site for CO2 storage. They will have done a baseline survey, and the baseline survey will have 3D seismic and a whole set of other observations of the seabed. But what we need to think about is how we efficiently, effectively monitor CCS complexes over the life of the complex, of the injection. So that could be 25 plus years. So the sorts of things you would definitely do after baseline is you'd obviously do in well monitoring of pressure and temperature. You're likely to do targeted monitoring of relic wells using landers equipped with active acoustics and chemical sensors. You probably will consider some wide area monitoring using autonomous systems to keep the cost down. Now, something else you may do in terms of looking at the reservoir is use spot or 2D seismic monitoring of the overburden of the top of the reservoir to see if you can detect where the plume has moved. The traditional approach has been to propose multiple 3D seismic surveys. I personally am not greatly in favour of this due to costs and their environmental impacts. And I think we need to be smart about the way we do long-term monitoring, not only to keep the costs down, but also to be friendly to the environment. So we need to, and many regulators and companies and academics are thinking around this, as to what type and what is the best MMV plan to propose over the lifespan of these fields. And I'll stop there. I don't know how long I've taken, but I'll stop there.
Thanks a lot, John. We have only 2 talks today, so there's more time for questions. And if you have one, type it in the chat or raise your hand. And we already have one question. Derek, go ahead.
Hi, John. Thanks very much. I was wondering, like by law, how big an area do you have to monitor around the reservoir?
So it's really that's a really good question. So you're supposed to the regulations are not clear. There's an EU directive, but you are supposed to monitor above the storage complex. Given these storage complexes are many hundreds of kilometers squared, that's a big job. So the directive says you need to be able to monitor and be able to detect, but it isn't prescriptive. So all these companies are interpreting how best to do it.
Okay, but I guess if there's lateral migration outside of the reservoir space, that could be an issue. Also, if you've got like 2 neighboring companies that have neighboring reservoir blocks, and there's a leak in the middle, like how will that be sorted out?
So this is something that they're really active. So in 2 neighboring blocks, and this is actually going to happen very soon in the North Sea, where you have neighboring blocks with separate storage complexes, you'll clearly measure the reservoir pressures and injection pressures in the different areas. But the legal framework whereby if you detect a change in, or you suspect there's a risk of a loss of containment, that's all got to be worked through. So the governance of CO2 storage is emerging. So certainly in Europe, there's a lot of work going on by regulators currently around this. And indeed, one of the limits to, or things that's slowing down the rollout of carbon capture storage is around the governance.
I have another question. When you start monitoring the seafloor, many things can happen. How can you make sure that there's no CO2 coming out that is completely unrelated to the storage site?
So in MMV, one of the key things is you need to be able to attribute. And that's something we spent quite a lot of time doing. And certainly injected CO2 is likely to have a different isotopic signature to natural CO2. Companies can also choose to dope their CO2 with a particularly distinct tracer to be able to do that. So there's a large amount of work going on, this is both for onshore CO2 storage and offshore storage, to be sure that you don't pick up an anomaly that's actually just natural variability. So that is something people are acutely aware of.
Okay, interesting. These chemical tracers could also be used to discriminate between neighboring blocks.
Yes, exactly. And you can get samples of reservoir fluids to be able to say this particular reservoir in this region has these isotopic characteristics.
Okay, Derek, again.
Yeah, just what are sort of the main strategies for the land-based CO2 stores? How does that differ to the marine monitoring techniques?
So land-based, there's a lot of work going into, I guess, chemical sensing, particularly of fluids. So that there's a lot of work going on around that. People also using essentially sometimes fairly continuous seismic monitoring. So putting down fiber optics into boreholes, and then shooting using things like variations on the fiber size beam in terms of having a known source signature and shooting to the well and looking for detecting changes. So some similarities. I guess the offshore, certainly in Europe, is likely to be the primary type of storage. I'm not so sure that's true in the US, but certainly in Europe, we're dominantly going to be looking offshore for our CO2 storage.